The broadcast is now starting. All attendees are in listen-only mode.
Hello, thank you for joining us for this session, Dreaming the Future, How Zero Net Energy Design Can Transform the School Environment. I'm Connie Umphris, Communications Manager at New Buildings Institute. Before we begin, I have a couple of housekeeping things to tell you about. First, you are muted and we cannot hear you. This helps keep the background noise down so that everyone can better hear the speakers. I want to direct you to the dashboard that you should be able to see on the right-hand side of your screen. If you are having technical difficulties and cannot see the slides or hear our speakers, you can use the question pane in this dashboard to let us know, and we will help you as we go. Please ask questions in the same question pane as they come up. We will have time to ask questions at the end of the presentation. At the end of the session, you will also be given the opportunity to take a short survey. Please take a moment to answer the questions as it helps shape upcoming events. This will also be your opportunity to give us your AIA number for the 1 credit that's being offered for this session. The session is also being recorded, and the link to the recording and a PDF of the slides will be sent in a follow-up email tomorrow. I'd like to pass it over to Amy Cortez, our Program Director here at New Buildings Institute, who will introduce our topic and speakers. Amy?
Hello, everyone. Thanks for joining us. I'm Amy Cortez. I also have Riley Loveland here for our Dream the Future webinar. This is the second webinar in a series of 4 that we are doing on behalf of the California investor-owned utilities. So we'd like to take a minute to thank Pacific Gas and Electric, San Diego Gas and Electric, Southern California Edison, and Southern Cal Gas. These investor-owned utilities are sponsoring this webinar today about the benefits of zero energy schools. New Buildings Institute, for those of you who are not familiar, is a national nonprofit that works to improve the built environment for people and for the environment. We have 3 primary program areas, and this webinar is about zero energy market development and leadership. For those of you who are able, there are AIA credits based on these learning objectives, which I won't go ahead and read, but we want to be sure that if you are eligible for AIA credits, you are able to get them by participating in the webinar. So thanks for being here. So I'm going to do a quick introduction to Zero Net Energy and then pass it off to Riley and our other co-presenters today. So when we talk about a zero net energy building, we actually are talking about a source definition that takes it back to the transmission and distribution. So it includes the energy that's used at the site, but also back to those transmission distribution sources. NBI maintains a database of buildings that have either achieved or are pursuing zero energy, and schools are a leader with 37% of the list. So it's pretty clear that zero energy schools and educational facilities are ahead of the pack. And when we're talking about schools, it's not only K-12 schools. We have community college examples, higher ed. Sometimes it's a simple facility, like a library facility or a science building on a school. So I think it's important to note that on the path to zero, you don't have to start at the entire school, but you might do a smaller building that's on a school site. Our research has shown that there are some pretty clear steps to success in sustainable design that achieves zero energy. All of these projects have worked hard to get stakeholder support, to have a clear commitment on behalf of the owner, to use a whole building integrated design process that tries to balance loads and minimize the energy load, and then use efficient equipment to deliver the services to the building. All of these buildings use an energy target, and this is beyond a % better than code, but really looks at an absolute energy number, and that's expressed often in energy use intensity. So the teams use design and construct to that target. So this is energy is considered at all phases of design, and then the handoff to make sure that the building is operated at a zero energy performance. So we find that measurement and verification is also something that happens rather than just being predicted to perform at a certain level. These buildings are actually operated, measured, and verified to perform at that level. We have put together some messages for particular stakeholders that really talk about the value and benefits of zero energy, cost avoidance by lower operating costs and utility costs. These buildings have all the attribute of sustainable high performance buildings, which is shown to improve student performance. These buildings are often used as a learning tool in and of itself. So a living laboratory, so there are educational benefits associated with these zero energy schools. We've also found that zero energy schools can be a place of refuge and for the community and when we're thinking about resiliency. So it's important to note that the zero energy schools are a good resource for the community for that purpose as well. And then finally, we've learned that while zero energy might be where everyone is headed, it's a path, and not everyone's going to get there on at every step. So it's important to leverage opportunities as they happen. So there are a number of tools that are available. So these are a couple New Buildings Institute developed tools about assisting design teams and school staff on how to use some of these communication messaging. Also a project guide which provides checklists on things to do and when in the design process they might happen. There are also a number of case studies that were developed by the California investor-owned utilities. So, so all of these case studies are available at the link that you have on the screen. And the Department of Energy, also U.S. Department of Energy has a zero energy design guide, which provides technical details on how to achieve zero energy performance. And there's also a resources hub, which has policy examples or examples, requests for proposals, or other mechanisms that school districts have successfully used to achieve very low energy and zero energy results. So we want to make sure you are knowledgeable about all of these resources that are available to you. So this webinar is really about using the school buildings itself as a tool to enhance student learning. And so I'm going to pass it off to Riley Loveland today to talk a little bit about how that works.
Hi, everyone. This is Riley, as Amy said. So resources to improve student learning are continually being developed and evaluated. So what if we could use these school buildings themselves as this tool to enhance student learning? High-performance schools like these zero-net energy schools can shape the educational landscape and dramatically make them for the better. So when you're engaging the stakeholders, as Amy mentioned, or talking to the school community, it's always good to keep in mind that the building itself is this opportunity for education, because we know that these buildings are about educating students and not about running facilities. So tying the building operations to the curriculum is a way to bridge the gap, the operations gap, and create these as these hands-on learning opportunities. Students then can become skilled and savvy in our technologically advanced society and develop this strong skill set that interweaves into our 21st century needs, like teamwork, research, time management, and the use of these high-tech tools. So tying the curriculum to the actual building and student behavior and occupant behavior helps promote this next generation of environmental leaders. And I just wanted to quickly include this slide because these are just some of the next generation science standards that are aligned with a very basic energy module that NBI has used with some schools. And when you're aligning standards with the building design and operation, you have this opportunity for increased buy-in from key stakeholders. And most importantly, students are more likely to be able to understand and retain the concepts that are being taught to them with those hands-on applicable learning opportunities. And in our research at NBI, we've experienced the link for buy-in between facilities, school occupants, and energy efficiency is this educational piece, because schools, again, are not about running facilities, they're about educating the next generation. So with students spending approximately 1,000 hours per year in a school, transforming the classrooms into these healthy and productive spaces is of our utmost importance, especially when the short-term and long-term health effects of students and staff is at risk. Our speakers are going to dive into this a little deeper, but studies show that students in these daylit, well-ventilated spaces perform better on tests, have healthier bodies and body mass, and attend school more days per year. So one story I like to tell really quickly is about students under the age of 16 and their developing brains. So we as adults are able to understand the underlying message of a sentence or of something we're being taught, often if we do not hear the full sentence. But children's brains under the age of 16 do not have the portion of their brain fully developed that is able to fill in those gaps in sentences when learning audibly. So with something like a noisy, inefficient HVAC system in the classroom, students are missing valuable learning opportunities. And then often teachers turn off these noisy systems to avoid this scenario, which lead to stuffy and uncomfortable learning spaces. There's a wealth of data out there about the benefits of these high-performance zero-net energy schools and how because of this, we need to drive our building design standards to be much higher for the benefit of our students, teachers, administrators, and ultimately these future leaders will have the power and the knowledge to better our world. So with all of that in mind, I'd like to introduce our two presenters for today. Teresa Pistocchini is the engineering manager at UC Davis Western Cooling Efficiency Center, and she has 10 years of experience in applied research in energy efficiency in buildings, primarily in the areas of heating, ventilation, and air conditioning, HVAC. Renji Chan is a research scientist in Indoor Environment Department of the Environmental and Energy Technologies Division at Lawrence Berkeley National Laboratory. Her work focuses on pollutant transport between outdoor and indoor air and implications to human exposure as a result. So I'd like to take a quick moment to let all of you also know, before we jump into that, of a couple other in-person workshops and webinars that we have coming up. We'll be hosting a Prop 39 workshop, a Zero Net Energy workshop in Oakland in 2 weeks on June 26th at the East Bay AIA. This is centered around stakeholder engagement and making the business case for Z&E schools. There will also be a Southern California Technical Z&E workshop in October in Pasadena. And we'll have 2 additional webinars in the fall. And check back on our website for the descriptions and more about those. You can see the link right here on the screen. There are lots of additional resources for you on your path to Z&E, and let us know how we can help, or take a look at these resources here to help drive your high performance goals. And again, these slides will be available after the webinar, as long also with a recording, so that you can pass this information on to your key stakeholders. Without further ado, thank you very much. And I think I pass it off to you, Renji.
Teresa, are you taking it first?
Sure, I can start. Okay, so today we want to specifically talk about ventilation when considering designing efficient or zero net energy schools. And so we want to talk to you today about research that has recently been sponsored by the California Energy Commission's EPIC program. And this is a partnership between the University of California, Davis and Lawrence Berkeley National Laboratory. How do we change slides?
Just let me know and I'll change them.
Okay, next slide. So our agenda today, first is to talk very specifically about the importance of ventilation in classrooms. And then we want to talk about how you actually achieve that ventilation and how you get compliance when you're doing HVAC replacements. Because really the way that we're going to get to zero net energy is not necessarily through new school construction, because that's a very small percentage of the market, but it's going to mainly come from retrofit and replacement in schools. And then lastly, we'll tell you about some technology opportunities in carbon dioxide sensing and demand control ventilation systems. Next slide. Okay, I'm going to hand it over to Renji now to talk about the importance of ventilation.
Thanks, Teresa. Next. So that we're all on the same page, we're talking about building ventilation today. Ventilation is the supply of outdoor air into a building. You may see a rooftop unit on a classroom, or you may see a wall mount unit, and both two will have an outside air intake, bringing outside air into the classroom. Next. So why is building ventilation needed? It is needed for comfort and satisfaction. If there's no ventilation, you will notice the classroom being smelly and stuffy. Ventilation is also needed to maintain good indoor air quality. And what we meant is there are emissions of indoor air pollutants from building materials, furnishing, things that students bring into the room. And so it's important to remove those indoor air pollutants using building ventilation. And as I will show you later, it is also important to support the health and productivity of the students and teachers. Next. Our group have recently done a literature review on ventilation in classroom. And what we see is that when you increase ventilation rates, we see literature studies from various research studies showing an increased student performance, a reduced respiratory health effects, and reduced student absence. So throughout this presentation, I'm going to show you some examples of what we found and how to convince you that ventilation is very important. Next. And talking about ventilation, sometimes we talk about concurrently about CO2 concentration. And the reason why we talk about this is that carbon dioxide, CO2, is what we breathe out, and so it's a useful proxy for estimating ventilation rate in a classroom. So this is one example. It's data that we measured in an ongoing project that I'm working on with Teresa, where we have low concentration in the classroom before the kids arrived. And as you can see throughout the day, as the kids arrived and as they go to lunch and go on break, you can see how CO2 concentration tracks with occupancy. In this particular case, we see concentration above the 1,000 ppm level, and that's an indication that this classroom does not have enough ventilation. We also look at the duration of the exceedance. So for this particular classroom, there's a long period of time that is exceeded this 1,000 ppm. So this is another indication that this classroom does not have sufficient ventilation. So measuring CO2 is a convenient way for us to estimate what ventilation rate is in a classroom. Next. And as I mentioned, we recently completed a literature review, and we look at what CO2 concentrations were reported in various classrooms in US, in Asia, in Europe, and across the board, we found high concentrations well above the 1,000 ppm level. So this brings home the point that oftentimes existing classrooms have issues with ventilations. There's not enough of it. And I'm highlighting a few cases where the concentration exceeded the 5,000 ppm level, and that's the level that OSHA set for workers. So if we don't think that's a healthy level for workers, we shouldn't be putting kids in classroom with such high concentration. Next. To summarize, in the review study, we look at 11 studies that measure ventilation rates and student performance. And in 8 of the 11, so the majority of the studies show a statistically significant improvement in some measures of student performance when we increase ventilation rate or as we lower CO2 concentration in the rooms. And you may ask, well, how do you measure student performance? So in some study, we use standardized academic achievements test. So we look at the ventilation rates measured in a range of classroom and how students performed in standardized academic tests. And also in some cases, the researcher will administer some computer tests or other ways to measure student performance. Next. So this is one example of how they measure student performance. So in 5 out of the 5 cases where the researcher changed the ventilation rate, measure performance, and they see an increase in performance at the increased ventilation rate. So the researchers may measure the speed and accuracy in how students perform addition, do some math, addition, multiplication, or they may measure logical thinking using some computer tests, or there will be some, they may administer some reading and comprehension tests. And as we change ventilation rate, we see that across all the intervention study that did that, an improvement in student performance. Next. Now, this is one example where the researcher increased the ventilation from 1 liter per second per person, which is not adequate, to 8, which is roughly what the ASHRAE standard is. And as a result of that, CO2 decreased from the 3,000 level to the closer to the 1,000 level. And across the board, in this case, the researcher used a computer test. So they measure the improvement in various types of tests that they do in terms of word recognition, picture memory. You can see that there's a clear improvement in how students performed. Next. Now, improving ventilation rates can also help with health symptoms. And health symptoms are harder to measure. Sometimes we'll use questionnaires. We have students fill out questionnaires, whether they experience symptoms like coughing, dry eyes. And sometimes the researcher will administer some tests to measure respiratory health. But these studies are harder to do. So we did still see 8 out of 11 studies reported statistically significant improvement. But the strength of the study is a little bit lower than the performance study that we did. We can see in the literature. Next. And I want to mention one study that we did, that we look at the association of ventilation rates with student illness absence. In 4 out of 5 study, there's a correlation. So more ventilation rates, we see a reduced rates of absence. And I want to go in the next slide talk about one of the study that we participate in. Next. And then this is a 2-year study that Lawrence Berkeley National Lab did. We follow 162 classrooms in all 3 areas of California to try to capture the differences. We measure the daily absence rates. We know the demographic data of the classroom, and we know the CO2 levels. And what we observed is across this 162 classrooms that have higher ventilation rates show a lower illness absence rate. And our hypothesis is that ventilation affects the long-term susceptibility of the students. And so this explains why we see higher ventilation rates. A classroom that are better ventilated show lower absence rates. Next. And as part of this study, we try to estimate what's the benefits of bringing classroom to have adequate ventilation rates from 4 liter per second, and that's not adequate, to what the code requirement, Title 24 ASHRAE has similar requirements of 7 liters per second per person. So yes, there's going to be an increase in energy cost, but the benefits to the school district, because as we understand, school revenues is tied to the student attendance rate. And also when we think about the reduction in caregiver costs, like parents have to miss work and so on to take care of a sick child. So those benefits will largely outweigh the costs. Next. So to summarize, we think it's based on research that we've done and others have done through our literature review. We're very convinced that providing adequate ventilation is important to keep students alert and focused so they can learn. And we're expected to see fewer respiratory symptoms and illness absence as we classroom have adequate ventilation rates. And the flip side of not having enough ventilation rate, we think that students are tired, they don't concentrate as well, and we see an association with increased respiratory symptoms and illness absence. Next. It's important to talk about, as we bring in more outside air, the outdoor air is not clean in many parts of California. And particles, fine particulates, you may hear the term PM 2.5 or fine particulates. That is a concern in some parts of California. I'm just showing a general map where we see high PM levels, the health effects associated with high PM. And you see some parts of California lit up in the in the darker area. So it is a concern. But and next slide. But one way to deal with that is to use high efficient air filters. So we recommended bringing up your ventilation rate to meet code, and at the same time consider using higher efficiency air filters. So MERV 8, I think, is a basic requirement. Going to MERV 13 if your school is located in the highly trafficked areas or areas where the outdoor air quality is often poor. And I think that's my portion. I'm going to hand this back to Teresa.
Okay, so now I'm going to, now that Renji has convinced you that adequate ventilation is very important, I'm going to talk about how you practically achieve that in HVAC replacements. So next slide. Okay, so I just want to talk about our study. We had a two-phase study, and the first phase of our study looked at schools that had recently replaced their HVAC systems. And so I want to talk about just specifically single zone HVAC replacements, which include wall mount and rooftop units. The majority of California classrooms are generally single zone, so one system serving one classroom. And so, yeah, so next slide. Okay, I'm talking specifically here about California ventilation compliance. Hopefully the message is you know, the message though can be applied to other states and other regions. California's building energy efficiency standards, Title 24 Part 6, specifies ventilation requirements for the state. HVAC replacements must comply with these standards, even when the replacements are like for like. So for example, if you remove a wall mount barred unit that's 4 tons and you put on a new 4-ton system. And in California specifically, the Department of State Architect, the DSA, oversees school construction, but HVAC replacements are generally DSA exempt. And so what happens here is that the school board assumes responsibility for exempt projects and for ensuring Title 24 compliance. So I just wanted to point that out explicitly here. And so this process is called exempt concurrence, and there's a DSA document on their website that explains that. Next. Okay, so the thinking is, do I need to worry about this, right? So we went to classrooms 104 classrooms that had recently replaced their HVAC system. So we weren't involved in the replacement in any way. We went and identified these schools after they had the replacements done. And we measured CO2 concentrations in those classrooms as an indicator of ventilation rate. And if the ventilation was adequate, you would expect to see the CO2 concentration below 1,100 parts per million. And so what we ended up finding was that 65% of classrooms had elevated CO2 levels, even though they had recently, purchased new equipment and had it installed and basically, generally thought everything was working well. And so the colors here on this bar chart, this is just one example school that we went to. And we also inspected the HVAC system to identify some of the reasons why the systems weren't working. But you can see in 4 classrooms, the ventilation system was not functioning at all. And so the orange bars suggest that that's less than half of the ventilation required by code. And 6 of the classrooms had this working ventilation system, but it wasn't configured correctly, so it wasn't providing a high enough ventilation rate. Next slide. So where does it go wrong? So we spent a lot of time looking at why 65% of those classrooms didn't have adequate ventilation, and there's a whole host of reasons. And so I just want to go through all of those so that when you're considering HVAC replacements as part of your zero net energy plans, you can think about how to not make these mistakes, basically, in installing your systems. So there's basically four things that have to go right. So one, you have to select equipment that is capable of providing ventilation rates for for high occupant density classrooms. So classrooms have a lot of people packed in there, so you have to make sure equipment is capable of providing enough ventilation. So that's basically step one. Step two, you have to make sure your ventilation equipment is installed correctly and then accurately connected to the control system, meaning essentially that all the wires are connected in the right place. The third step is commissioning and acceptance testing. And this is kind of your fail-safe. At the end of the day, once the system is all installed, and I'll talk more about this, acceptance testing is required so that you have to set the ventilation system settings to make sure that they're delivering enough air, and then you have to measure it. And then lastly, you have to maintain and operate the system so that filters must be changed regularly, and then teachers need some instructions on how the system works as well. Okay, next slide. So just briefly talk about what's required in a classroom in California, which, as Renji mentioned, is similar to the ASHRAE requirements. But basically, you need 15 cubic feet per minute of outdoor air per occupant. And if we assume, obviously, it can vary quite a bit, but if we just assume for today that a classroom is designed for 30 people, then that is 450 cubic feet per minute, just to give you an idea of the magnitude of how much air you need to move. Next slide. So then there's various types of ventilation equipment that you could purchase. So there are a couple pieces of equipment that do not work well for that. It's impossible to get 450 cubic feet per minute of air through them, basically. So in a first case, so you can see the picture on the left, we found at one of the schools, this is a spring-based damper that opens when the fan turns on. And this is a piece of equipment designed more for a data center. So like a data center doesn't have people in it, you don't need a high ventilation rate, and so this wouldn't work for a school application, but yet we found some of those in our study. The second design is a fixed inlet. So there's sort of a large hole here that allows the air to come in. But one of the issues is that you need to be able to shut that if needed. And the other issue is there's no path for the exhaust air to go out. So if you bring 450 CFM into a classroom, you have to be able to exhaust air from it, because otherwise you would be pressurizing the building. You might have issues with the doors, and you just basically the fan won't even be able to move that much air because of the pressure difference. So really the most simple system that will work is a motorized damper, and I show this damper up here is in a barred wall mount unit, and basically the damper opens and closes to when the system turns on, the damper opens, the ventilation air comes in, and then it exhausts the air as well. And you have to be able, you see some, I mentioned setting the system correctly. The system doesn't necessarily ship from the factory with the right setting, right? It might be set for a data center, or however they set it. And so the installer or commissioner has to go in and set you can see these letters A, B, C, D on the top right. And so they have to set it correctly for a classroom. Next slide. In order to improve efficiency, there are some other technology options. So once you have a moving damper, right, you can think about how you want to control that damper to best to increase efficiency. So really common, especially in California and in milder, like coastal areas, is to use an economizer. So an economizer basically measures the temperature of the outdoor air, and it uses outdoor air for cooling when the outdoor temperature is low. So because the cooling loads in classrooms are really high just because of that high occupant density, so it's often colder outside than it is in the classroom, and so you can use the outdoor air for cooling. And then the last piece of equipment I show here is kind of interesting. This is a barred option for ventilator option for their equipment. It basically has an enthalpy wheel, and the exhaust air, the heat is recovered from the exhaust air and used to either pre-cool or preheat the outdoor air going into the classroom. And in a current phase of study that we're doing, we're actually doing it was an intervention study where we went and actually affected the type of equipment that is installed. and we're monitoring it very carefully. So we're doing a very detailed analysis of the energy performance of both energy recovery ventilators and economizers, specifically for classrooms, portables. Next slide. Okay, so once the equipment is selected, some thought needs to be given to the control system. So what the California code says is that you have to supply that minimum outdoor air rate when the classroom is, the entire time the classroom is occupied, and 1 hour before occupancy. So there's a couple of ways you could do this. You could have just local control via a programmable thermostat, or you could have an energy management control system to schedule the ventilation system operation district-wide. In the recent study we did, where we looked at retrofits in the past 3 years, energy management control systems were very common. So I just kind of show some pictures here. This is just one example of Delta Controls and the programming interface. So EMCS is really powerful because now you can essentially watch what's happening in the district and set district-wide schedules, but you do have to be extremely careful that everything is hooked up correctly and that everything is programmed correctly. Next slide. So what tends to go wrong is that all the schools are ordering all the equipment at the same time and trying to get it installed in the summer before school starts. So there's like a huge demand, I know it from BARD to deliver these systems, and they can't, right? So everything's way up until the last minute. And so, you know, it's a picture we took at one district of, you know, the guy working like the week before school starts, and I think this is very common. And so what happens is that you know, you got to get heating and cooling working because you need your students to be able to go to school. And so you get the system up, but the question is, in order for the ventilation to work, it has to be installed, powered, and connected correctly to the control system. It has to have the correct damper settings programs, and you have to have the right settings in your EMCS. And so those are a whole bunch of steps past, you know, the fact that the heating and cooling is working. And so that's, I think, really what schools are up against. There's a lot of work that has to happen after that system, you know, gets put on the building. There's very little time. Next slide. So what is supposed to happen is that schools, well, everybody in California is supposed to do commissioning and acceptance testing of ventilation systems. There are various procedures for how you do this. I'm not going to go into that in detail. There are forms that are supposed to be filled out for every system that's installed. Compliance rates with acceptance testing in general in the state of California are very low. I don't know exact numbers, but that's my understanding. So, you know, just point out how this is, you know, very, very important, but doesn't tend to get done. And so that's why we believe we see so many of these problems in recently installed systems. Because essentially this is like your last defense. So if you go to do the acceptance test and it fails, you know something went wrong. Either the wrong equipment was purchased, it wasn't installed correctly, the damper wasn't set correctly, whatever. Next slide. So I just want to talk a little bit about what acceptance testing looks like. And so this is basically one of our engineers measuring the outdoor air flow rate going into the classroom through the outdoor air intake. And so what needs to happen is you need to measure the outdoor air rate for each unit and confirm it's within 10% of the design. So within 10% of likely that 450 number I mentioned earlier. Could be a little different for different applications. Confirm the control system is programmed correctly, ensure that ventilation, heating, and cooling are all functioning. And I also just want to point out, I don't go into it in detail in these slides, but we also, as part of this study, we surveyed teachers and we asked them all sort of questions about their perception of their indoor air quality. And then we correlated that to the actual CO2 levels that we measured. And it turned out that teachers are actually are not accurate reporters of their indoor air quality. So it's very, very hard to detect. It's very subtle. It has a big impact, right? We've shown it has a really big impact on student performance, but you cannot really tell. that it's not working and that the CO2 is high. Like you cannot perceive it like you can perceive that it's too hot or it's too cold. And so it's kind of this underreported, not very well detected problem. And so that's why it's so important to measure. Next slide. But on a follow-on to that, one way, if as you're considering replacing HVAC systems, really strong recommendation to include CO2 sensors in your thermostats. So particularly if you're already investing in an energy management and control system, most of those manufacturers sell various models of thermostats, and pretty much everybody has one that includes a CO2 sensor. So here is a display in one of the classrooms that shows, you can click the little temperature button or the CO2 button, and then the CO2 is displayed to the teacher if they want to know, and that signal is also sent back to the EMCS system. So this is a really obvious, this tells you right away if you have a ventilation problem. So if the contractor and the commissioning agent didn't get the thing installed properly and didn't commission it properly, you know right away. And the CO2 sensing isn't particularly expensive, and so I think that this is a very worthwhile investment. So then from there, the other thing you can do is you can also control your outdoor air damper to respond to the CO2 level, and that's sort of a next step. You still have to maintain some minimum ventilation all the time, but what you can do is you can save energy when ventilation isn't needed. So basically, when the kids go to lunch, the damper can close slightly if CO2 is low, or if the kids are at an assembly, or maybe the control system just didn't get programmed correctly and it's running on a school holiday or a teacher work day, for example, when the classroom is there's only a couple people in there. So this has a lot of options, or enables a lot of functionality. Next slide. In our study of recently retrofitted HVAC, recently replaced HVAC equipment, we did go to 2 schools that actually had demand control ventilation systems implemented, different manufacturers, different equipment. And in those cases, so you can see on the left are the mean CO2 concentrations of those classrooms. And so the left bar is the classrooms in the study, which were 21, that had demand control ventilation systems. And so you can see that that ventilation rate hovers right around 600 to 1,000, which is really the desired range, which is the balance between providing adequate ventilation and then also saving energy. I mean, it's possible to overventilate. It's not that likely in a classroom just because there's so many people in there. And then on the right-hand side, you can see the rest of the classrooms that did not have demand control ventilation. We also separated them by classrooms with economizers and classrooms without economizers. But you can see generally here's where that the CO2 range was really significant, and here is where we saw really high CO2 levels. Again, because you don't know. Whereas with the demand control ventilation systems, all those classrooms had CO2 sensing, and we generally found that it was very effective at managing CO2 levels, and we didn't identify any hardware or control problems with those installations. Next slide. Lastly, back to the maintenance piece that I mentioned, that's the last step. Dirty filters can reduce airflow and reduce ventilation rates, and also reduce your system operating efficiency. So just picture on the left, that's what you want to see. Picture on the right, not really what you want to see. This is, when we were talking to districts, the cost, not necessarily the cost of the filter, but the time involved in filter replacements is significant. And schools have a really hard time keeping up with filter replacements. And we just want to reiterate that it's also really important to make those investments in maintenance as well. Next slide. Last piece, I mentioned that we surveyed all the teachers. 1/3 of teachers said that the noise from the HVAC system interfered with the learning environment. And so it's also, generally speaking, there are different fan models available in your purchase, and looking at those fan noise ratings is important. Because in a worst case scenario, the teachers are advocating for their fans to be shut off, and you need to have that fan running all day. And so, you don't really want to make the choice between like providing ventilation and like being able to hear the teacher. So fan noise is really important. Also need to educate teachers on why the fan is running. We found that most of them didn't understand that the fan is providing ventilation. And so one of our goals as a result of the study is to create some educational materials that can be shared with teachers. Next slide. So it's a summary of our recommendations from what we've seen from our study over the past year. So absolute must in equipment selection, make sure ventilation equipment is appropriate for classrooms. Second, consider an energy management and control system to manage system-wide schedules. Then from there, if there's extra resources, consider quieter fans. Consider CO2 sensing thermostats to quickly detect ventilation problems, and consider demand control ventilation systems based on that CO2 sensing signal, which will close the damper in response to the CO2 signal. Lastly, for installation and commissioning, again, I mentioned in California, the school district is ultimately responsible for compliance. So ensure that the contractor bidding process includes acceptance testing. I just put a link to like an example, suggestions for a bid sheet, or some things to think about when preparing contractor bids. And then actually ensure that the contractor performs the acceptance testing. So collecting and keeping those completed forms is really important, because generally speaking, it's a little bit of a gut feeling, but it seems that the contractors sort of know when that maybe they won't be asked for that, and so they skirt on some of these installations and don't finish the job basically. And then lastly, on maintenance and operation, educate teachers on the necessity of fans running, and then also consider MERV 13, use MERV 13 filters and change them regularly, which is on the order of every 3 months during the school year. Okay, next, I think. Oh, so one of the things that you might be thinking about is if you've had previous installations done, now you might be kind of wondering what the situation is at your district or your school. And so the things that you might consider is going back and asking a contractor for a previous installation. They should have done all this acceptance testing and they should have set all these settings. So asking for their ventilation rate measurements, asking for their acceptance test reports is a good idea. Second, if you have a if you're a fairly large district and you have a facilities team, consider investing in an outdoor air measurement flow hood so that you can actually check ventilation rates yourself. And lastly, there are various just off-the-shelf sensors you can buy to log the CO2 in a classroom for a day, just to see what the situation is. I mean, this could also be useful if you have a teacher that's complaining or is concerned about indoor air quality. We haven't gotten very far with it yet, but we've also thought about that could be sort of an interesting, Riley was talking earlier about student learning experiences. So that would be an interesting thing to possibly, that students could look at and measure too. Next slide. And that's it. So questions for us. And then I also, if you're in California and you specifically want to understand more about the Title 24 compliance and acceptance testing, I also listed the Energy Standards hotline as well.
Okay, so this is Connie again, and we will start with some questions. And just to clarify, you will be getting a follow-up email from us tomorrow with a link to both the recording and the slides, so you can either forward them along or re-review at your leisure. So our first question is, can you please explain how increasing ventilation rate results in, please explain how increasing ventilation results in higher revenue for the school district?
As I understand, this is Renji. When we did the study, the school get paid on attendance. So you have a lot of kids missing schools, your revenues go down. So that's how we calculate that, that relationship.
Okay, thank you. Did you check classroom noise from the HVAC systems?
We tried initially, but we were often the problem was that we had to work around the school trying to get into these classrooms after school, and too often there were teachers in the classroom or janitorial or whatever, so we just couldn't get. Obviously, we would need a really quiet environment to actually measure fan noise, so we relied on the teacher's report of whether fans were too noisy or not.
Okay. Are there any good studies of the impact of ventilation for student dorms?
I'm not aware of anything like that. I would think that would be, I don't know what your thoughts are on Renji. I mean, obviously ventilation is important in all cases, but I would think that that's less of a risk of being a problem just because the occupant density isn't quite so high.
So for student dorms, they've been looking at overnight CO2 levels affecting sleep quality. I think there's some study coming from China on that. So it's like a different issue because, you know, usually college students are away from the dorms during the day and then they're there at night to sleep. So they tend to look at the different aspect of health effects.
Okay, thank you.
I also want to mention something else really important related to ventilation. So it doesn't seem like we actually mentioned in our presentation, but one of the issues that's really important is that, you know, there's also natural ventilation, right, from opening windows or from infiltration just in building leakage. And one of the things that's happening is new construction is getting tighter and tighter. So the importance of a functioning mechanical and ventilation system goes up as you increase the tightness of your building shell. And we didn't look at that closely in our study here, but that's sort of a current trend that's very important to keep in mind.
So we have a couple technical questions on the HVAC side. How adequate are smaller fan motors for pulling air through a MERV 13 filter? Can this cause premature motor burnout? And then what about using the MERV 11 on a smaller fan motor?
Teresa,
you want to go ahead? Right. Well, okay. Let me just say specifically that generally speaking, in smaller HVAC and in packaged units, you're going to have ECM fan motors, and ECM fan motors are designed to provide a constant flow rate. Basically, I mean, obviously there's limitation, but against any pressure drop. So as the filter gets, if you put in as the filter gets dirty, the fan works harder and works harder to keep providing a specific flow rate. What that does is it ends up using more energy. So I think as long as you're within the range of the manufacturer's specifications, but up to MERV 13 generally is probably fine. We are looking at that more closely in the study that we have going on currently, where I mentioned we're looking at different ventilation systems. We're also comparing MERV 8 to MERV 13 filters from both an indoor air quality perspective and an HVAC system performance perspective.
Yeah, well, when we look at filter pressure drop, we see a range. A MERV 8 filter can have the same pressure drop as a MERV 13 filter. It's just depend on the design of the filter. Is it highly pleated or is it not highly pleated? Is it 1-inch filter? Is it a deeper filter? So it really depends. It's not really, right to say a 13 filter must have a much higher pressure drop. Not necessarily.
Okay, thank you. We have a couple questions regarding the both the materials, the educational materials that Teresa mentioned at the end of her presentation, as well as about the summary of the research that was presented. Where are those available to our participants today? Or are they available yet?
Yeah, at the moment, our actual technical report is still sort of back and forth with the Energy Commission. So at the moment, all we have is this slide deck. But I think what we want to do is put this information into a case study, and then also make some education materials for teachers. So we don't have those things ready yet. I don't know if maybe when we do, we can send them out to NBI and you can send them back out to the mailing list or something like that.
Yeah, we could do that.
This is Riley from NBI. I'll hop into that. We, in those tools and guides that Amy mentioned early on, we list a lot of the information, list a lot of the sources for the information that we mentioned in particular. So we'll provide a bibliography of the data that we mentioned, and we'll touch base with Teresa and Renji about getting their data also onto that bibliography so you all can see where that comes from.
And feel free to send an email just if anybody has any specific questions or wants some advice for their specific application.
Okay, and then kind of probably the last one we have time for today. All of this information is very technical. How do I communicate it to a school board?
Well, I think that the most important pieces, I think, are the importance of ventilation and how that relates to student performance and absence rates. I think that's a very important message for a school board. I think then, that essentially gets the funding for the projects, but it's really the facilities department. It's not that we're not seeing these HVAC replacement projects get funded, it's that we're not seeing the quality of installation actually deliver what's needed. So I think that's really more of a message for the facilities group, who has some technical understanding, that will then ensure that their staff and their contractors follow through and get the technology working as it's intended.
This is Riley from NBI again. I would throw in too that NBI has a stakeholder messaging guide that translates some of these more technical pieces of information into groups like the right stakeholder group and who might be more interested in this, and then how we can effectively communicate with them. So I would suggest looking at that, or again, just touching base with Renji or Teresa or us to discuss how we might be able to doctor some of the messaging towards your specific stakeholder group.
Okay, anything else, Riley, before we close out?
I don't think so. That was great. Thank you so much, Teresa and Renji and Connie and Amy. It was a great group today.
Thanks everyone for your time today.
Thank you.
Bye.